SwayamPrabha. Digital India. Educated India.
Okay, last class we looked at interfacing using Tiva Launchpad for the PWM interface. Okay, so how do you run the motor by using PWM interface? We took an example of Tiva, but that can be extended. The syntax is different, but the philosophy remains the same. So the same thing can be extended to any other microcontroller as well. Now today's class we are going to look at interfacing of encoder by using this dedicated quadrature encoder interface, QEI interface in Tiva Launchpad. So again here we'll introduce first this philosophy of like how these encoder interfaces they work, typically what kind of registers or control registers are there for like getting these interfaces done. And then we'll look at a little bit more details about programming using Tiva Launchpad. And further than that, we are going to look at also the sampling time. How do you set up the sampling time in the mechatronic system working? Okay, so microcontroller needs to have some specific sampling time for the system to work. Okay, why, all those kind of things we will discuss in the class. So let's get started here. As you know, this working of incremental encoders we are just recalling, we have seen it before. So what happens is we have just the slits in the wheel, and then you have this light source and light detector, okay, photodiode, and this light source and detector, they work in pair, and when the light passes you get pulse. Okay, light passes through that, and then this slit passes the slit cuts the light, you get a pulse. Okay, and then we know that okay, there are two sensors needed, A and B, to sense the direction in this case. Okay, so these two outputs A and B are 90° out of phase with each other. How they are made 90° out of phase? By their proper placement with respect to each other. Electrical domain, like you don't need to have them so closely spaced. One can be sensing here and other can be sensing somewhere else. Since all the slits are uniform, you'll get 90° out of phase all the time. And we may use another sensor to get the position, absolute position of the encoder peel. Okay, that is called index pulse. Okay, it is typically termed as I or Z. So we know that these are the pulses that we get, and in one direction you will get this kind of a pattern of the signals, in other direction you get some other pattern of the signals. And A and B signals, they are to be processed in some way to read these patterns and get encoder output. Okay, so this is what encoder the any circuit for decoding this, they do, they recognize this pattern, and then they produce some pulses corresponding to each of these phase, or each of these kind of a combination of A and B. And so then the pulses are to be counted to get the encoder count. Okay, so that is how the internal circuitry would be designed or positioned to count these pulses, and then change the direction. Based on change the direction, the count up or count down would be changed. Okay, and then the direction change will be sensed by saying, okay, look, after 0 0, if there is 0 1, then there is a clockwise direction, and after 0 0 there is a 1 0, then there will be anti-clockwise direction. Something of that sort, some logic will be used to get the direction sense. Okay, so there are many advantages of using these incremental encoders. As we have seen, they are digital output sensors, so they are noise free, so there is no noise error in these signals, and small amount of noise, if at all that is there, that can be also taken care of by some filtering, as we will see in this QEI interface of Tiva. Then it has a quadrature output, 4x kind of output. So 4 pulses will get per one hardware slit. Okay, so this is what will happen. Like, these are the 4 kind of signals you will get in one cycle of A, for example. Okay, or of one cycle of B, so to say. So one slit will correspond to 4 pulses. That's why it is called the term quadrature. Okay, this is a quadrature output. And then you get a very accurate speed estimation by looking at time between 2 pulses, or number of pulses in a specific amount of time. Okay, that's a way you get very accurate estimate of the speed in these encoders. Okay, there are 2 ways. One is look at the time between the 2 pulses, or you look number of pulses in a given amount of time. Now, how this is up and down count is done in Tiva, how the speed can be estimated, we will see in detail for the Tiva interface. Okay, so as we have seen, this interface is for up and down counting of the incremental encoders as the position changes for the encoder, and then also for the speed estimate. Now, see, in the absence of this interface, you would need some kind of a circuitry to do this job. Okay, so if you are interfacing encoder with, not with Tiva but any other kind of a microcontroller, and that doesn't have this QEI interface, okay, then what to do? Then you'll use this chip called HCTL 2021. That HCTL chip is going to do this job of what this interface is doing. So basically, idea is there is some kind of a clock. Based on the clock, you will take these inputs A and B and process them internally to, as I said, to generate 4 pulses per one kind of a cycle of A, and then those 4 pulses, or those number of pulses, will be counted by using some kind of a counter. Okay, and that up and down count will be changed based on the direction, direction logic. Okay, so this is how this interface will typically work, and we will not get into the details of logic circuit to do that and all, but we just need to kind of understand that, okay, it will have to take inputs of this A and B and process them in some way to kind of get you the count. So this will happen in QEI interface, which is already there in the microcontroller circuit itself. It is part of the microcontroller. So you don't need any extra chips as for Tiva kind of a microcontroller if you are using this interface. So there are 2 modules in Tiva for QEI. So you can interface 2 encoders in Tiva. Okay, and each of the module has input signals A and B, and index pulse also is input. So 3 inputs are provided in each, and typical features are there is a position integrator to track the encoder position. Of course, it should give us a position. That's what we are interested in. Then programmable noise filter is there. Okay, on inputs A and B and Z, you can have some kind of a noise filter to be applied. Then velocity capture that is done using some built-in timer. We will see how this velocity capture is done, and the input frequency can go as high as up to 1/4 of the processor frequency. Okay, so this is really fast kind of a interface. So see, so then you can capture very large amount of speed, or a very high speed data can be captured. Because higher the speed, the number of pulses coming, you can see would be much more quicker. Okay, so for example, if you see these pulses that are coming, higher the speed, this time duration between the 2 pulses of this A or B is going to start reducing, and it may reduce at some very high speed to some extent that you may not be able to count that fast. Okay, so that's a limit that is given here. Okay, 1/4 of the processor frequency is what. So if you have 50 megahertz processor frequency, typically 12.5 megahertz will be the frequency of input. Okay, so that is pretty high. I mean, depend upon encoder, of course, the resolution you are using. If you are using encoder with a nanometer kind of a scale resolution, then your speed will get limited. Okay, by this number. Okay, but if you are using micrometer kind of a resolution for the encoder, then I mean, I am talking of linear right now, but it is applicable in the rotary case also as well. Okay, so higher speed, if you want, like you need a faster kind of a microprocessor to get that higher speed encoder readings recorded. Otherwise, you'll have a trouble. Okay, otherwise you'll miss out or you'll lose the pulses, and when the pulses are lost, then your count will not be faithful. So if you are using only the speed kind of application, there are some different kind of ways one can do this operation. You don't need, then depending upon how fast your speed application is, you can just make use of index pulse only to do the speed monitoring. Okay, if your speed fluctuations between the two kind of index pulses or within the rotation are not too many, not bothering to your application, then that can be done. But for all the robotic applications, you will need accurate positioning, where you are interested in not just the index pulse, but you are interested in entire speed of the robot from starting to end kind of a trajectory. Then you'll have to have plan your hardware, I would say, to do these high speed kind of measurements faithfully. Okay, then there are additional features where there is an interrupt generation is also possible. So you can generate interrupt on index pulse. This will be useful for resetting your encoder value, for example, in any case. So say for example, if you have a robot kind of application, it's a homing or zero position, okay, of that robot, on the power up can be done based on this kind of idea. Then you have after velocity timer expiration, there is some kind of interrupt generation. So these are these kind of different possibilities for interrupt generation. Direction change happens, you generate interrupt. Then phase signal error here, then in that case you can generate some interrupt to kind of halt your application or something like that. Okay, so this interrupt, how we can use it, up to you to use this, but this is a facility that is provided by the interface. Okay, now let's see a little bit more detail of this interface in Tiva. So there are two phase signals, phase A and phase B, that's what they call it. N is like channel 1, channel 2, something, and they can be swapped before interpreted by the module. Okay, so this is an additional facility that is provided in Tiva. See, many times it happens like, okay, when you say rotate the encoder, you see, look, to set up things properly for our mechatronic system to work as what we do in our normal calculations or mathematical model, the positive voltage given to the motor, okay, should result in positive displacement. Okay, many times this may not be true based on your hardware connections. Okay, so if that is the case, then we need to just swap these phase signals, okay, two phase signals. Then what will happen is for positive, suppose for positive rotation, like the count is actually going down, or count is counting down, then by swapping, you can correct for that. Okay, that is a facility that is provided in the so to correct some miswiring of the system is what they say. Okay, so you miss in the wiring, so you can correct it by checking the wiring and doing it correct wiring also, but this is a software facility that is provided by the interface to avoid the drudgery. Then input signals will have this digital noise filter, that filter can be enabled by using this bit in this control register. So see, these are the kind of registers that you need to look for for doing this, using this facility. Okay, so if you want to filter, like use noise filter, then you use this kind of a bit in this control register, and you will get that facility. So we'll see there are two again, as we said, saw in the case of PWM. There are two kind of a ways of philosophy of programming. Okay, and two ways of programming, that both ways can be okay to kind of go ahead with. One is like based on these registers, understanding how these registers work in the case of Tiva in particular here, and other is by using API libraries that are provided by the manufacturer. Okay, so we saw that philosophy and how that can be used in case of PWM. We are going to look at similar kind of a thing in the case of this quadrature interface today. Then the mode of operation, okay, that can be changed. There are so this you can see what are the modes of operation that are available, but that can be changed by using some other kind of a bit in the. So there are this kind of a description will be given, and then this module block diagram is given. Okay, so this, how do you read now this block diagram? Okay, how to make sense of this? Okay, so you need to read a little bit of a data sheet. See, these are these names that you see here. They are basically registers. Okay, QEI stat is a status register. QEI CTL is a control register. Then some like kind of a timer load register is there. Then you'll have these signals are coming and getting into this some kind of a some circuitry which will give us output of the direction and number of pulses. So phase A, phase B, like for one cycle it will generate 4 pulses here, and those pulses are going to get kind of counted somehow up and down, and the output will be available in this QEI pose kind of a register. And these are the kind of a ways one can think about reading this. Okay, then there are this interrupt control that is there here. So some bits to kind of do this interrupt control. Some control registers to do that interrupt control. Okay, so this so you need to see what are the inputs out of these, what are the outputs, and see whether, like say for example, you can set this QEI time or QEI load kind of a register. Okay, and this QEI count and QEI speed are the results or outputs that are to be seen actually. Okay, so these are the output registers. QEI pose is again output register. QEI max pose is where you can write this maximum position beyond which, like this counting will get reset. Like that, there are some things. Some of these things, like I am telling from reading the data sheet, but you can also find out like these register details, and you can start making sense of such diagrams. Okay, then we'll have a little more description now about these. Okay, so so this after swapping, like the signals are coming up here. Okay, so these are already swapped signals. Okay, so swapping algorithm is somewhere like something will be there in the control. Okay, so then let me get this. So then we have this more description of about it. So position integrator block is what is using these signals, as we saw here. See, position integrator is here. It uses these signals which are processed by this quadrature encoder, and then directly gives us this position in the QEI pose register. Okay, so see, this is so easy. I mean, so I don't know if you have an experience of reading encoder, but we had done it as a part of some other kind of activity, and where to interface that HCTL chip to get to this point where you are actually start reading these. So you need to have this circuitry in place. Okay, so you need to connect wires, you need to have a hardware or design some PCB, and then get that HCTL chip to interface. Instead of that, in Tiva it is happening all internally done. You just need to program it and start using. Okay, so this way it is so easy if you have this kind of an interface that is directly available as a facility for a user to program in the microcontroller itself. Okay. So this is good to use this encoders, this kind of a microcontrollers which will have this QEI interface for many mechatronics applications. It will be very useful. Because encoders are what, like, give very accurate kind of position estimate. We have seen because of low noise, and it is that's why it is more kind of a prominently used in mechatronics applications, and that's where these interfaces or microcontrollers with these interfaces will become important for the mechatronic engineer to develop some applications. Okay, then velocity capture is using a configurable timer and a counter register, and then the timer counts number of phase edges in a given time period. So if you see this block diagram, like this is this number of these edges. So this, say we have seen that, okay, these are these on this line you will have some pulses which are coming based on the phase A, phase B signals. Okay, so these pulses will be typically 4 pulses in one kind of a cycle, and these pulses will be counted for a given amount of time, and then you'll know that, okay, this is the speed. Okay, so that is what is being done, and then there is some kind of a velocity pre-divider which will be available in the control QI control register. You can set this pre-divider value so that you get some kind of a facility of reducing the number of counts to do some accuracy, or like to make sure that the numbers don't overflow the register that are used to store them. Okay, so this is how this philosophy of velocity capture works. Okay, the timer will count the number of phase edges in a given time period. Okay. Now, how do you set up this time period for capturing? It is a QEI load register. Okay, so this count in this register will count the number of clock cycles which are there for, and then this QEI load. Suppose like I have QEI load value to be 100. So 100 clock pulses is counted before the timer is before this timer is reset. So for that 100 clock pulses, we see how many edges of the microcontroller, how many edges of the encoder phase signal they are counted. Okay, or how many counts of encoder happen in the 100 kind of a value of this QI load. Okay, so QI load, when it is 100, it will count 100 clock pulses. So that much is the time that is given for this timer. Okay, that's how one can think about. See, typically this comes from, like, you cannot say, okay, I'll give some microsecond or millisecond kind of a time in this timer. No, that time is not typically given. So everything in the microcontroller happens with reference to the clock. Okay, so if the clock is running at, say, whatever frequency, number of clock cycles is what you will typically say as a time. Okay, so this, when timer load register, this is, see, so typically we'll deal with all integer values in these registers. Okay, if you think carefully, like, all these values that we are dealing with are integer values in the register. So you cannot say, like, some unit time. You say that unit in terms of, like, number of clock cycles, that will be like a integer value. So that's how, like, you specify typically in the microcontroller philosophy these different values of registers. Then the count is also pre-division of the velocity count will be possible, which can be set in the QI CTL register. Okay. And then this value, current value, will be available in QEI count register, and once this is timer is finished, then that value will be transferred to this QEI QEI speed register. So this count is current value, and once the timer is finished, that value will be transferred to QEI speed register and it will be available till the next time it is getting reset. Okay, so current speed will be taken from this QEI speed register. Okay, and then depending upon how fast you want to update the speed, you can put a counter, put a timer value accordingly. Okay, now let's see how do you find the speed of motor shaft in RPM. Okay, if the counter specifications are known and relevant register values are known. So this is a question that you need to ponder over. Okay, I'll leave it at this point. You think about, suppose I have a motor which is using 1024 kind of a counts in one revolution, or 1024 slits for the one revolution of the motor. That is the encoder specification that is given. Okay, so we have 1024 slits. Okay, so quadrature will have those many number of counts, 1024 into 4 counts will be there. Okay, 4096 counts will be there. Now these kind of counts are coming, and then we want to know what is a motor RPM. When we have set up we know the clock signal coming at some frequency, and we have set up timer for some duration, time duration, and in that time we are counting how many number of pulses are coming. Then based on some simple mathematics, you may be able to estimate this value of a motor RPM. Okay, so think about how will you do this. Okay, maybe we can have this as an assignment or quiz problem, exam problem. Okay, then you have, again, as I mentioned, two ways to program QEI interface. Okay, first is register based programming. Okay, so I'm giving you some reference here also, so that you can go to that page 1310 of this microcontroller data sheet that we have shared. Okay, and in that you will find all the details of these different registers that are there. Okay, and steps that are required to be done to program this interface. Okay, and second way is using API libraries. Okay, so this again these functionalities of this API library are provided in the syntax of API. That is again another data sheet that is provided. So typically microcontroller manufacturers will provide you with these data sheets of the details of this how this microcontroller can be programmed. In some cases you will have this API library files. In some cases you will have to work with only this register. For XCP, for example, for XCP100 kind of a microcontroller, we have only the this register based programming happening, and in Tiva you have possibility of both. And see, these API libraries are nothing but, if you see these functions, if you see the function details, you will find the same thing, these functions use finally the register based programming. So this is the base level programming, register based programming. Okay, now typical steps that are used in programming this QEI using APIs are, first you need to have these library files available. Okay, and initialize these are important so that you make use of the functionalities that are provided. Okay, and then initialize some variables that you want to use in the system. Then for initializing hardware, these are the steps for QEI to be followed. So configure clock frequency. This is the typical step for many interfaces we need to do. Then enable this module. Okay, this peripheral module enabling some functions will be there to you use them to enable the module. Then now see, if you see this map of the pins of this Tiva microcontroller Launchpad, in this there are programmable GPIO interfaces which can be changed to act as a QEI interface, or it can be changed to act as some other kind of a interface. Okay, so we need to, before we start using it as a QEI module, we need to tell microcontroller that okay, look, I want to use this particular pin provided for the QEI kind of a module. Okay, so for example, D port has some pins which are used for QEI module. Okay, we need to enable those particular kind of ports, and then further map the pins to act as a QEI. Okay, so this is done, this GPIO pin type is to be defined in some function. So this is a function that is given for making these pins to act as a QEI pins. Then pin configure, you configure these pins for A, B or index kind of a pins. Okay, so these are the kind of typical steps that will be given. This is all given in the function library data sheet or manual. Okay, so you need to find these functions, how they are working, what is the input output, and all those details you need to find, and you'll get that. So see, I'll give just kind of a brief of some of the things, but you can go ahead and look at this particular, you can just search for this function, okay, in the whole data sheet. Otherwise the data sheet is too huge. So to find, like, you can get into QEI interface and then start reading some of the part, and then you maybe, if you want, you can search for this particular kind of a phrase, and then you'll be able to get the details of that particular function. And of course you will have sample programs available that also kind of make quite a bit of sense. Once you have this hardware initialization part done, then you go to QEI module functions which are used for QEI module programming. So this is one of the first thing you need to do is a configuration. Okay, so you look at this function configure, QEI configure, and see it can be configured for mode of operation, swapping the input channels, required or not required, the maximum position value, all these kind of things will be put in this function QEI configure. Then filter enabling you may need to do, okay, if you want to use filter. Okay, then enable the QEI module also by using QEI enable kind of a function. Then you'll do some kind of a configuration of velocity capture, so by using this function. So pre-divider, timer, those kind of things you can set by using this velocity configuration. And then once this configuration is done, the QEI velocity module also is QEI velocity part is also enabled, and QEI is enabled, then you'll be obtaining position in this QEI position get function and QEI velocity get function. Okay, you want to get the direction, you can get this in this QEI direction get function. Okay, so these are the ways you can use these functions to get you the desired output of QEI position. Okay, so this makes our job quite simple. Okay, so by directly using some functionalities, you are able to now read encoder and start using that encoder data for further control kind of a programming. If you want to use PD control or some kind of other kind of a control using this data, you will be able to do that very easily now. Okay, so we have seen PWM, and we have seen now this QEI interface, in which by using this now one can start thinking of building entire closed loop system. Okay, we'll talk about that a little bit, how do we build a closed loop kind of a system by doing that. Okay, so this is just a kind of classification of all these different pin functions. Okay, and this is a sample program. You can see this part where you have to initialize, add these libraries and get this set up here. Then some of the variables, if you want, whatever you want to use, you can initialize the variables in here in the main program, and then you can initialize hardware, and you follow the steps that we just saw. Okay, so if you see, some of these functions are doing this hardware initiation basically here. So you are mapping the pins, configuring the GPIO pins to act as as an index pulse or a pulse or B pulse and things like that. Okay, and you are enabling this QEI 0 module, you are enabling this GPIO D register. Okay, so port D we are enabling to kind of make sure that the pins of port D which are used for QEI interface are enabled and things like that. Okay, then you are doing this configuration of this QEI interface here, and you can see these are the details of the configuration register, QEI configure. Okay, you do all these different configuration parameters to be set here. Okay, and then you enable QEI interface. Okay, this is particularly QEI 0 interface. There are QEI 0 and QEI 1, 2 interfaces will be there. Then velocity configuration you are doing here. Okay, and once this is velocity is configured, now you will be able to start reading it. Okay, so get QEI position, you say position is equal to QEI, so this is from function 0, you are using 0, so this is from interface 0 with this function. By using this interface 0 value can be fetched in this position. So QEI position get of QEI 0 port or QEI 0 interface, you will get encoder position of encoder which is connected to this pins corresponding to this QEI 0 interface. Like that you can have a position QEI 1 interface position also. So if you are using 2 motors at a time, you can use this other interface as well. And then position, you get position, velocity and direction. Okay, so this is how typically you go ahead and get writing the program to get your QEI module working. So I would suggest that you should try this yourself with this QEI module and the Tiva Launchpad that you might have procured by now, and already started exploring different interfaces. So use our motor in the kit to do this kind of a programming and get a feel of how things are happening, and that's the best learning that will happen. If you have doubts, things you can post, and the TAs and we can help out with those things. Okay, so this is how this module is going to work. Now next we'll look at how do you put together now entire things now. Okay, on the programming side of the microcontroller. Okay, the theory part we'll look at in the future classes to come, but we can now start putting things together once we know how do you get the position of the motor, and once we know how do you run the motor. Okay, so we have seen both of these. So what is needed is now to put together. So what we typically need to do is to run this three operations in a sequence. Okay, first is a reading of the sensors or reading of encoders, then computation of the control knob based on the encoder feedback position and what we want. Okay, and then finally using this control knob computation, you get some kind of a U or output that is going to the motor, that is to be implemented on the motor actuator. Typically actuators will be actuated through PWM, and then PWM duty cycle is what will change every sample time, so to say, or every cycle. Okay, these three operations will go on in a cycle. Okay, they will keep on repeating with some kind of a time interval. This time interval called the sampling time. Okay, so this is a very important concept in mechatronic systems, that you will have some kind of a fixed sampling time that is to be set, so that these operations successfully get carried out every time interval of the sampling time. Now this time interval needs to be fixed, because there are digital implementations of filters that happen typically in this case, and they depend upon sampling time. Okay, so all the digital implementations of the filters will have dependence on the sampling time. Okay. So sampling time is very important to maintain in the system. How do you maintain that? One of the ideas to do that is how do you set up that, okay, or how do you maintain this sampling time, is to write entire program and find the execution time that it takes for this program to run. Okay. And once we know, okay, this is, let's say it takes 1.5 milliseconds as a time to run the entire program, and I want to set 2 millisecond as a sampling time, then I know 0.5 millisecond needs to be a delay. Okay, so I'll put some additional delay, that is by doing some kind of a delay function, and keeping microprocessor busy in some kind of a addition operation in a loop for that much duration, and after this delay is performed, then again it can start doing this next operation, next cycle. Okay, so this keep on happening for an infinite loop. That is one way of setting up sampling time. But the disadvantage is that there is no flexibility in changing the program easily. You need to change program, you need to change the delay also. Then there are conditional statements, if they are there in the program, if else kind of a program, then it will change sampling time. So it's a cumbersome way, and then you are keeping your microcontroller busy in doing some delay function, okay, which is of not much of a use. It just kind of keeps microcontroller busy, so as to kind of have you give even that much kind of a delay. So there should be a good way out of this. We need to use some other way of doing things here, and that way is basically by using interrupts. Okay, so we recall the philosophy of interrupts, where say suppose you are reading a novel, okay, and your mom calls. Okay, so you are sitting and peacefully reading the novel, and then the call comes. Then you hear the bell ring, and then what you do, you put a mark in your page wherever you last you are working there, and finish the call. Of course, if you like to. Many times you may not like to take a call, but let's say if you want to take a call, and you finish the call and come back again, start reading the novel. Okay, that is what you do. Okay, exactly the same philosophy is there for the interrupt. When the interrupt comes on some pin, then microcontroller halts whatever it is doing right now and serves something, and run some small other routine that is to be that is programmed to run when that interrupt comes, and then again comes back to the main program after finishing that job. Okay, so this is a kind of a philosophy of a interrupt that we have seen, and if we have this when you come back, you may do nothing, you may just wait, but to wait for the other signal to come. So that way, that much time is available for microcontroller now to do some other activity if it is to be done. Okay, but now the idea is, now if we get these pulses coming on this pin in some kind of a periodic manner, okay, then this same operation can happen again and again and again and again whenever these pulses come. Okay, so idea is to use a timer to generate this interrupt pulses every few milliseconds, or every whatever sampling time that is needed. Okay, so if you want 2 millisecond kind of a sampling time, you generate this pulse every 2 milliseconds, one pulse comes. Well, this pulse is connected to interrupt pin, and that interrupt pin kind of receives this pulse, and once it receives the pulse, like it starts executing some program, which is your program, which is doing these 3 operations that we talked about: reading the encoders, like computing the control, and implementing to the actuator. Okay, so this is how it really happens. So that's what we have seen, that we'll generate the pulses every sampling instance or every sampling time, and this pulse will trigger the interrupt and start running program called this program that we run, where we have these 3 operations are done. Okay, these 3 operations that we are writing. Somebody can write any other kind of a thing in that interrupt service routine. Okay, but that program is called interrupt service routine. Okay, so this is interrupt service routine is a name that is used, ISR. So this is a terminology you need to be aware about. and the program starts running. Once the program is finished, it will return to the main program. If there is any activity remaining to be done in the main program, it will continue, otherwise it will just wait for the next pulse to come. Then in Tiva, this is done using again API functions, okay, and this interrupt service routine is simply predefined name function. So nothing needs to be done in the hardware. So all the things in the hardware are somehow connected in whatever way it is needed, and you don't need to kind of worry about that. Okay, you just need to use a timer and then enable that timer for interrupt kind of operation, and that is it. Your job is done. So we'll see some of the steps here, but the idea here is to do this timer setting. So typically you'll say, okay, oh, this timer setting will have what all things to be done. Okay, I need to set a time. So I should look for some thing where I can set up the time. Okay, then I should look for that okay, this timer needs to be connected to this interrupt. Okay, so it is interrupt enabled timer should happen. Okay, and then I need to run this ISR. So I need to look for what is ISR. So ISR in this case will be simply some predefined name function, in which in that function if we write something, that whatever we write in that function, that will get executed every time the interrupt is happening. Okay, so this is how you set up the sampling time in the modern kind of microcontroller applications. Okay, so if you are very high fidelity, or I would say much better kind of operations of closed loop control can be achieved by using this sampling fixed sampling time set up by interrupt based philosophy, rather than just using continuously in the loop without really giving any attention to what is the sampling time happening in your system. It's better to kind of understand what is this we set, what is the sampling time we want to set, and that much sampling time is set properly for the application. Your application is going to run much better with a higher performance. Okay, so this is typically some functions that are used. So this timer load set is a function used to you can look at this function, search for that, and read the function in API library data sheet, and see what are the arguments to this function and what it does and things like that. Now for this this is an example for timer 0. This timer load set function will have these arguments to be used, and then this is a period to be set according to sampling time. So you have again the same philosophy that okay, so sampling time, for example, to be 0.1 second or 100 millisecond with frequency or sampling frequency to be 10 hertz, then this will be set this value. This is like a period value that is set based on the system clock, whatever is the system clock frequency divided by this 10 minus 1. Okay, so this is how this number which is to be loaded in the it's like a loading that is happening in some register. This number will be registered in some load, and it will be count to 0, and then the pulse will be generated. That's a kind of a philosophy, the same way it is used as in the case of timer in the QEI module. And this is a sample program that you can look at. So this is a peripheral enabling happening for the timer peripheral enable, then configuring this timer, and then you are setting some kind of a timer frequency, and then you are enabling here interrupt enable. Okay, so interrupt enable happens here, then this timer interrupt enable, some interrupt enabling functions are there, and then the master enable function happens, and then you enable the timer for the timer 0, that is what you are using for the interrupt. So these are some functions. You need to read through the details of these functions, what they are doing, and understand and start making use of them. Okay, and once you set up this interrupt kind of a routine, then you need to look for what is the function in which I should write my interrupt service routine. Okay, where and how do you look for that? Okay, so the interrupt service routine in this case is this particular kind of a name, okay, timer 0 interrupt handler, okay, and in this function you write some kind of statements. So first statement that you will write is this clear of this interrupt. So this clearing is doing some clearing of the interrupt mask, okay. This is done so that now the interrupt is ready for the next pulse to receive. So if the next pulse arrives, then like this will again start reading. If you don't do this command, then the operation is run once and it will just kind of wait, because the clearing is not happen. This clearing is important to happen. So once the clearing happens, then one can the next pulse comes again. This so this command, if you miss, then like you may find that okay, your system, your program is not running. You will wonder why. So this is important concept here, the clearing of the interrupt mask. Okay, so this is how we'll go ahead and put together the things now to really read the encoders, then compute control and write PWM duty cycle value. And now how do you compute control based on the dynamics and the control, some of the theoretical aspects we'll look at and give some kind of a practical implications of some of the theoretical results, and then we'll discuss how do we now so we are here basically getting ourselves completely ready now to implement any kind of a closed loop kind of control with a microcontroller. So some theory we'll look at, and again we can kind of come back and do this programming, or parallelly we can do this programming for some of the mechatronic applications. That's how we'll go ahead. Thank you very much.